Hey everyone, Mr. Hauk here. In today's video, we're going to be proving the addition formulas for sine, cosine, and tangent. So using our knowledge of the unit circle and what we've learned previously in the course, we're pretty familiar with the values of certain trig functions. For example, we could easily use the unit circle and right triangles to find the sine of 60 degrees or the cosine of 150 degrees. But what if we needed to find the value of a trig function of a less used angle? Or what if we needed to find the value of a trig function for a sum or difference of angles? Well, that's what we're going to be exploring today in this video. We're going to be proving the addition formulas for sine, cosine, and tangent. And in the next video, we're going to be proving the difference formulas for sine, cosine, and tangent. In order to do this, though, we're going to be using a special geometric construction, which you can see right here. So the way that this geometric construction starts is we start with the line segment AB. We revolve AB to the point C, and we get line segment AC, and the angle that it sweeps out is angle alpha. Then we take AC, revolve it to D, and we get the line segment AD, which sweeps out the angle beta. Okay. Next, we want to draw line segment DE to be perpendicular to AB. So I drew in this line right here. There's the point E. Notice that DE is perpendicular to line segment AB. Now, if you look at this right triangle right here, there's a couple things that we should really be able to notice. The sine of alpha plus beta is going to be DE over AD. We're going to be using this later. Also notice that the cosine of alpha plus beta, and again, we're looking at this triangle right here, the cosine of alpha plus beta is AE over AD. That's using our SOHCAHTOA, our right triangle trigonometry from first semester. All right, next, let's continue with the construction. Let's draw segment DF to be perpendicular to AC. So here's AC, here's point D. We draw segment DF to be perpendicular to AC. Next, let's draw segment FG to be perpendicular to AB. So here's FG. Notice it's perpendicular to AB. And then let's draw FH to be perpendicular to DE. So here's FH. Notice it's perpendicular to DE, so we get these 90-degree angles right here. Okay. Now I'm going to make the claim that angle HDF is equal to alpha. So HDF, that's this angle right here. So I'm making the claim that this angle is equal to alpha, this angle right here. Now, how can we actually get this? Well, notice that AB is parallel to HF. And since those two lines are parallel, this line segment AC cuts the parallel lines. So by alternate interior angles, this angle alpha is equal to this angle. So this is angle alpha as well. Now check this out. Let's say that we call this angle, let's call it X or something, some unknown angle. Well, notice that if this is alpha, then this chunk right here has to be 90 degrees minus alpha, because we have this 90-degree angle right here. So this is 90 degrees minus alpha. This is 90 degrees, which means that this angle, which we're calling X right now, is 180 degrees minus the 90 degrees from right here, minus the 90 degrees minus alpha from right here. If we go ahead and distribute the negative here, we get 180 degrees minus 90 degrees minus 90 degrees plus alpha. The 180 minus 90 leaves us only with alpha, so X, which is what we call this angle, has to be alpha. So it's a quick little verification that this angle right here really is alpha. And that's going to be important to us as we're proving the addition formulas. Okay? So this is our special geometric construction. And we're going to use this to prove these two results right here. So I'm going to make the claim that the sine of the sum of these two angles, the sine of angle alpha plus angle beta, is equal to sine of alpha times cosine of beta plus cosine of alpha times sine of beta. And I'm also going to make the claim that the cosine of these two angles added together is the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. Let's go ahead and prove these. So the first one we're going to prove is the addition formula for sine. So we want to prove that the sine of alpha plus beta equals sine of alpha cosine beta plus cosine alpha times sine of beta. Now recall from the construction that we made, you can see it right here, that the sine of alpha plus beta is equal to dE over AD. Okay, so now notice that dE is actually FG plus DH. And let's take a look at that real quick. So dE, this right here, is actually FG plus DH. And that makes sense, those line segments add up. So let's do a little bit of reorganizing. So if sine of alpha plus beta equals dE over AD, and we know that dE is equal to FG plus DH, well then dE over AD becomes FG over AD plus DH over AD. What we're going to do now is we're going to do a little bit of algebra manipulation. So what we're going to do is we're going to multiply FG over AD times AF over AF. Notice we're allowed to do this because AF over AF is just 1. So multiplying by 1, we're not technically changing anything. We're also going to be a little clever, and we're going to multiply DH over AD times DF over DF. Again, notice this is technically a 1, so we're not really changing anything. But let's now rearrange some things. We know that multiplication is commutative, so the order that we multiply in doesn't really matter. So I'm going to rearrange AD times AF to be AF times AD. I'm going to rearrange AD times DF here to be DF times AD. But watch how this is a little bit clever. FG over AF, let's find that real quick. FG over AF, well, if we look at this triangle right here, this right triangle, that's just the sine of alpha. Sine is the opposite, FG over the hypotenuse, AF. So FG over AF, that's just the sine of alpha. AF over AD, here's AF, here's AD, so we're looking at this right triangle. Well, AF over AD is the cosine of beta. Okay, next, DH over DF, so here's DH, here's DF, so we're looking at this right triangle here. Well, DH over DF is just going to be the cosine of alpha, because here's the adjacent, here's the hypotenuse. And then lastly, DF over AD, so here's DF, here's AD. Looking at this 90-degree triangle right here, that's going to be the sine of beta. Sine opposite, there's the DF, hypotenuse, there's AD. But that's actually exactly what we wanted to prove. Notice we started with sine of angle alpha plus angle beta, and we ended with the result that we wanted. Sine of angle alpha times cosine of angle beta plus cosine of angle alpha times sine of angle beta. So that's the end of our proof. We'll do a little box here and fill it in. That means end of proof. And we're done. We've proven the result that we wanted to prove. So what that means is for all future problems, we can use this to help us calculate the sine of two angles added together. Let's now prove the same result for cosine. So let's prove the addition formula for cosine. And what we want to prove is that the cosine of two angles added together is equal to the cosine of the first angle times the cosine of the second angle minus the sine of the first angle times the sine of the second angle. So recall from our construction, and again we saw this previously, that the cosine of these two angles added together was AE over AD. Okay? So notice that AE is really just AG minus FH, and let's show that real quick here. Here's AE. Well, if I take AG and subtract FH, then the result would be AE. Okay, so that's pretty easy to see. Now, let's start by saying, okay, well, let's take the cosine of angle alpha plus angle beta. We know that's AE over AD. And if we replace AE with AG minus FH, then AE over AD equals AG over AD minus FH over AD. And now let's start being a little clever with our algebra again. Let's multiply AG over AD times AF over AF. Again, this is equal to 1. We're allowed to do this. Let's also multiply FH over AD times DF over DF. Once more, this is equal to 1. We're allowed to do this. We're not technically changing anything. Manipulating some of these pieces, let's go ahead and switch the places of AD and AF right here. And let's switch the places of AD and DF right here. By doing that, let's look at the pieces that we get. If we look at AG over AF, here's AG, here's AF. That's just the cosine of alpha, because cosine is adjacent, which is the AG, divided by the hypotenuse, which is the AF. Okay? Now let's look at AF over AD. Here's AF, here's AD. Looking at this right triangle right here, this is the cosine of beta, because AF is the adjacent, AD, that's the hypotenuse. Okay, so cosine of beta. Next, FH over DF. So FH right here, DF right here. That's going to be the sine of alpha, because the opposite is the FH. The hypotenuse is DF, so that's sine of alpha. And then finally, DF over AD. Here's DF, here's AD. Looking at this right triangle right here, that's just going to be the sine of angle beta, opposite being the DF, hypotenuse being the AD. So we get sine of angle beta. And that's exactly the result that we were trying to prove. We started with cosine of alpha plus beta, and we ended with this right here. So, end of proof. So again, that means that for future problems, if we're trying to add, or we're trying to take the cosine of these two angles added together, we can use this to calculate. Okay? So now that we've proven those two results, we can also prove the addition formula for tangent. And what we want to do here in our last proof is we want to prove that the tangent of these two angles, alpha and beta, added together is equal to the tangent of the first angle plus the tangent of the second angle divided by 1 minus the tangents of the two angles multiplied together. Okay? Also recall that tangent is sine divided by cosine. The tangent of an angle is sine divided by cosine. We saw this in first semester with right triangle trigonometry. So that means that the tangent of alpha plus beta, well, since tangent is sine over cosine, tangent of alpha plus beta becomes sine of alpha plus beta divided by cosine of alpha plus beta. Well, we just did two nice proofs for both of these. So we saw that the sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. And we saw that the cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. So this is the direct result of the two things that we just proved. Now we're going to do again some algebra trickery, so to speak. Okay? So for each of these four terms right here, we're going to divide all four of those by cosine alpha times cosine beta. Since we're dividing all of them by the same term, it's not really changing the value of anything. These two are still equal to each other. The reason we want to do that is because we get, by doing this, this little manipulation here, we actually get some really cool things to cancel out. Notice that cosine beta are going to cancel. Cosine alpha will cancel. All of this is going to turn into 1. And then this piece right here, we're going to see it simplify. So let's look at what happens here. So the cosine beta cancels. We get sine alpha over cosine alpha. Cosine alpha cancel. We get sine beta over cosine beta. Here, everything canceled out, turned to 1. And then here, none of this could cancel. This stays the same. But remember that sine divided by cosine is tangent. So sine of alpha divided by cosine of alpha is really tangent of angle alpha. Sine of beta over cosine beta is really just tangent beta. Then you have the 1 minus. Sine alpha over cosine alpha, that's tangent alpha again. Sine beta over cosine beta, that's tangent beta again. And that is the exact result that we wanted to prove. and that's the end of our proof. So these are the three results that we just spent this time proving. These are called the trigonometric addition formulas or the trigonometric sum formulas. And now in the next couple of videos, we're going to be using these in combination with the difference formulas that we're going to prove in the next video to start solving some problems.